Lecture 22 series is about animation. Let's look at some fundamental problems in animation and the gimbal lock problem. Static objects are boring. Look at your project part 1 scene objects. They just sit there. None of the objects can move in an articulated way. Although you can move them from one place to another and rotate them and change their color, they're still boring. They cannot perform any movements. They're rigid objects. What if you could define more complicated and interesting objects that could move, such as living things or vehicles, things that can perform movement? These things are all made up of separate moving parts that are still part of the whole object. So wherever the complete object goes, its body parts goes with them. So if a human is moving, the arms of the human moves with them, but the arms can still perform individual articulated movements when the person is stationary. Let's look at how artists make cartoons or animations. They create a mesh for a game, a shape, a character, or a vehicle, define its geometry, fill in colors to define its texture, and then define the material properties. Either color it in, giving it a shiny appearance or a more diffuse appearance. And then they create animation sequences for different game states of that entity. Note that exporting data from modeling animation tools so that it can perform the same animation in another application can be tricky. This is part 2 of your project. Now let's look at a simple way of creating an animation. In a traditional hand-drawn animation, the senior key artist would draw keyframes, and then the junior artist would fill in the in-between frames. We can use a similar approach for computer animation. For a 30 frames per second animation, less than 30 keyframes would be needed, and the number of keyframes needed would depend upon how complicated the motion is. The data, which includes the joint angles of an articulated figure, are assigned to the keyframes. In-between frames are interpolated. For example, we have this box object that needs to be rotated by theta 1 degrees over here, but we don't want to go suddenly from this state to this state. We generate in-between interpolated frames so that the object moves smoothly from this position to this position, and in the in-between frames can be generated using a linear combination of theta 1 and theta 2, where the weight of theta naught and theta 1, where the weight of theta naught decreases as we move from here to here, and the weight of theta 1 increases. So theta naught sort of becomes smaller and smaller, and theta 1 becomes bigger and bigger until theta 1 is the only value that remains here. And the same goes for the x1 and y1 position of the object. Here is a simple animation example of a tank. The gun turret should be able to rotate. The barrel should be able to point up and down. The wheels should be able to spin. Note that the keyframes do not need to be equidistant apart. It depends upon the type of motion. So if you want to define the motion from here to here and then up, then you would define, let's say, the next keyframe where the turret has moved, rotated in this direction, and the keyframe 3, we would show that the barrel has rotated upwards in this direction. What would be the tank hierarchy? Recall your lecture on hierarchy. We'll have a tank hull. This would be the central parent section. We'll have wheels. These are the children of the hull and are siblings to each other. We'll have a gun turret. This is another child of the hull, which has yet another child, which is the gun barrel, and that is the only child of the gun turret. Thus, where the hull goes, the wheels also go, and the turret and barrel must also go. When the hull rotates, the wheels rotate, and all other children that are connected to the hull must also rotate. But when the gun turret rotates, only the barrel rotates with it. So animation must take into account the hierarchy of the object. Now there are problems with interpolating Euler angles. So far we have studied that rotations can be performed as combinations of Euler angle rotations which define pitch, yaw, and roll. These are also the rotations that are commonly used in Blender to represent complex rotation of bodies. Now in keyframe 1, which we call 1, 1, we have alpha 1, beta 1, gamma 1 that represent the pitch, yaw, and roll angles of a rotation. In keyframe 2, which we represent with frame number 2, 1, we have alpha 2, beta 2, gamma 2 that represent the pitch, yaw, and roll angles of another rotation. We have to compute these angles for frame 12 to 20. Now 11 is the actual frame number, whereas 1 is the keyframe number. And going from keyframe 1 to keyframe 2, we have to define intermediate frames 12, 13, 14, so on up till 20, so that we can put the keyframe 2 ahead of it. The in-between values have to be calculated through interpolation. Unfortunately, the Euler angles are problematic when interpolating, so we cannot interpolate Euler angles without ending up in problems. Unexpected rotations would result when we combine the three interpolated angles. Consider interpolating between alpha 1 is equal to minus 170 and alpha 2 is equal to 170. This type of problem is called a Gimbal lock problem. The second transform may align the first and the third, leading to 2 degrees of freedom rather than 3. Gimbal lock is a situation where a rotation accidentally brings two local coordinate axes into alignment and thus losing 1 degree of freedom. Then you're only left with 2 effective rotation axes rather than 3. This is a serious problem, as using the Euler angles to represent rotations that we are not able to rotate about one of the 3 principal axes, X, Y, or Z, when Gimbal lock occurs. Some useful YouTube demos and explanations about Gimbal lock are given at these references. Can we avoid Gimbal lock in interpolating rotations of keyframes if we want to remain using the Euler angles? Consider the 3 Euler angles, theta x, theta y, and theta z. We can use any 6 of these combinations. Either rotate about x-axis first, then about y-axis, and then about z-axis, or we can follow x, z, or y, y, x, z, and so on. So there are 6 possibilities. If one of them leads to a Gimbal lock, we can use another rotation. However, this does not eliminate the Gimbal lock problem. This only avoids the problem for a particular case. And another complication here is that since matrix multiplication is not commutative, the resultant rotation matrix is different for each order. So we will have to work out different theta x and theta y to achieve the same rotation. In the next mini lecture, we will see how we can solve the Gimbal lock problem.